First of all, I would like to thank the organizers for invitation. In this talk, we will discover some properties of F-divergences and discuss the applications of them. After a brief introduction, we will proceed to main inequalities governing the relationship between divergences and state two theorem, and in the end, list few applications. Let us first recall the basic notions of information theory. The first and the most important one is those of entropy, which has been introduced by Shannon in 1948. This quantity can be thought of as a measure of uncertainty contained in a random variable, and for a discrete case is defined in the following way. If a variable has some outcome with a low probability, then after observing with this outcome, we will be very surprised. And this is what is captured by this logarithm. So the sum can be thought of as an average surprise we obtain after observing outcomes of a random variable x. Later, this quantity has been generalized. And so we are now able not only measure uncertainty of one random variable, but also capture the information stored in it and also the amount of shared information between two random variables. The second important definition is a Callback-Leibler divergence. In the original work, it has been stated for a much more general case, but the definition will involve Redon-Nikodym derivatives, and so I omitted it. Usually, when we give such definitions, we use the following agreements, which govern special cases. So the sums are not infinite and are well defined in most cases. Some works concerning these notions and applications are listed here. Let's now proceed to the main part of our talk. The F-divergence is defined in a way similar to that of a Callback-Leibler divergence. In fact, it is a generalization of this notion. For a function f, which has some nice properties, we only need it for special cases of divergence, and so that we do not obtain zero here very often.
Excuse me, does it depend on mu?
Yes, it does and it does not. Usually the change of variables theorem for a Redon-Nikodym derivative is applied, and so the quantity resulting is the same. But however, we need to make sure that this measure mu exists and both measures are absolutely continuous with respect to it. Yes, but sometimes we have some more complex measures, for example, on functional spaces or singular measures and so on. The common examples of F-divergence include Callback-Leibler divergence, which we have already discussed. It's for a choice of f equals t logarithm t. A total variation distance, which is widely applied in a central limit theorem field, and a chi-squared divergence. Note that the last one can be defined by two choices of f, and both will result in the same quantity finally. Some properties define the niceties of this divergence, and they explain why we use them so often. Usually, the divergence is always non-negative, and it is equal to 0 if and only if p and q coincide. However, it is usually non-symmetric, and this is why we cannot treat it as a metric. The third quantity is usually referred to as a data processing inequality. If we have some channel which takes one probability distribution as an input and outputs another probability distribution, then it contracts the space of all probability measures, which is captured by this inequality. It is natural, since if we process some data, we usually lose some information. And so the details which enabled us to determine between two measures are lost, thus the contraction. And the final property is the variational representation of F-divergence. We will need it for our theorem, and note it involves the Legendre transform of F. we will compute it for special cases later. Now let's discuss two main divergences we will concentrate on in this talk. The first one is a chi-squared divergence, and it is usually not used per se. However, it has some nice properties which enables us to describe other divergences in terms of this one. And this is what is captured by this theorem. Note that a chi-squared governs the local behavior of other divergence, at least along some given segment in the probability measure space. Another divergence we will use is the Callback-Leibler one, but we have already touched upon it and we'll discuss some applications later. It is of great interest to compare different divergences because they are used in different fields, and so if we compare them, we can bridge the gap between two fields and bring together useful insights. The first and the most well-known one is a Pinsker inequality. It governs the relationship between Callback-Leibler divergence and the total variation distance. It has been improved by works of few authors, but this original formulation is still widely applied because it's very laconic and in its own way beautiful. And the second important relationship is between Callback-Leibler and chi-squared. Here is an upper bound. We will try to provide a lower bound for this divergence. The usual way of obtaining such inequalities is by means of joint range. We define a joint range for two divergences as a subset of R2. That is just points which coordinates of which correspond to the values of divergences for some probability distributions. And similarly, we define a restricted joint range. All the same except for distributions are on a finite subset of a natural numbers. The main theorem which governs this approach is that of two Norwegians. I don't think I can recite their surnames clearly. It tells us that the joint range of two divergences is just a convex hull of a restricted joint range of order 2. So instead of computing this quantity explicitly, we can just parameterize the R sub 2 and take a convex hull. After we do this, we usually can derive some lower and upper bounds for divergences just by looking at the picture. However, it is not always possible to provide bounds in this way. More specifically, the lower bound for Callback-Leibler in terms of chi-squared cannot be obtained in this way. It becomes a trivial zero lower bound. In order to provide it, we need first to prove the following theorem by Nishiyama and Seison. It's just the relationship between Callback-Leibler in chi-square in an integral form. To prove this, first note that the logarithm of a non-negative number, positive one, can be expanded in the following way, by integral. This can be checked directly by integration. Now, introduce the following measure as a mixture of two measures p and q. Note that it will also have a Radon-Nikodym derivative with respect to the same measure mu, and densities can be expressed explicitly. Now, decompose the Callback-Leibler divergence by means of logarithmic expansion and change the order of integration. Expanding the inner expression, we will obtain two terms. The first one equals 0 because p and r sub s are both densities, and thus the integral across the whole space equals 1 for each. So we subtract 1 from 1 and obtain 0. And the second term can be expressed in terms of the chi-squared divergence in the following way. Just decompose the inner expression and obtain this. By definition of r sub s, we can rewrite the second argument and obtain another r sub vs. And now we can just substitute this into our integral representation, set s equals 1, and obtain exactly the formula which we wanted to prove. And now we are ready to provide a lower bound for callback library in terms of chi squared. However, it is not possible to do with only chi squared, which I have already mentioned. We need to incorporate different terms in this expression, and here the term is a third-order Rényi divergence. This is not an F-divergence in the sense we defined it earlier. However, the limit of Rényi divergence when the index tends to 2 will be a callback library divergence. So it also has nice properties and is widely applied in different fields. The proof proceeds as follows. First, apply the variational representation for chi-squared divergence. We can compute the Legendre transform for f explicitly by means of maximizing a quadratic polynomial. And f with star becomes this. Now apply again the variational representation and decompose the supremum into two consecutive supremums with this norm equals any norm on a functional space. This is again a quadratic polynomial with respect to lambda, and we can maximize this value. After maximizing, we will obtain the following in the inner supremum. And so the chi squared is lower bounded by this formula. And since we can take arbitrary norm of g, we can get rid of this condition for taking supremum and just obtain a simpler representation of chi squared. Now compute this quantity for R sub s from our theorem, more specifically from theorem of Nishiyama and Seizon. We will just take s away from the formula and denote those terms which do not depend on it by alpha, beta, and gamma. After computing the integral, we will obtain the following bound in a logarithmic way. Now substitute the g equals p divided by q minus 1. This is exactly the function on which the supremum of our lower bound for chi squared is obtained. Substitute the resulting quantities in alpha, beta, and gamma, and obtain that gamma and beta equal some function of chi squared. Alpha can be also decomposed, just a straightforward way, and we will obtain the terms depending on a Rényi divergence, chi squared, and a constant. Substitute this into our logarithmic bound and obtain exactly what we wanted to prove. Now we have some time left to discuss the applications of callback library divergence. I will not discuss all of them here because it's a wide field and we do not have time for it, but most applications are concerned with machine learning or computer science, and they are widely applied in similarity learning, reinforcement learning, causality studies, and other sciences. Let's concentrate on a variational autoencoder as an example. This is a widely applied model nowadays, model of machine learning, and we usually apply it if we want to generate synthetic images or some other samples of very complex probability distributions on a high-dimensional space. The model contains two parts, the encoder one and a decoder one. The encoder takes an image, a natural image, as an input and transforms it into a lower dimensional or sometimes higher dimensional latent space. After this, the decoder tries to reconstruct the original image from this latent vector. And now, if we want to obtain a synthetic image, we can just take some point in the latent space and send it as an input to decoder. However, if we just do this, we will usually not obtain a meaningful images, because not all the points of the latent space correspond to some natural pictures. In order to do this, we need to penalize our model with extra loss. And this loss is traditionally expressed in terms of callback library divergence. It's a callback library divergence between a distribution of vectors generated by encoder and a standard normal random variable in a latent space. And now, if we want to generate a synthetic image, we will just take a normally distributed random variable in a latent space, send it as an input to decoder, and be glad that we obtained a good synthetic image. Now we are ready to draw conclusions. First, I think I have shown that F-divergences are widely applied in different fields, and so the study of them is important for applications. It is also interesting to provide bounds and other descriptions of one divergence in terms of other. However, it is not always possible to do in a straightforward manner, which is described by a joint range theorem. However, we may try to overcome this difficulty by applying and incorporating different terms in our expressions and trying to minimize their impact on the whole formula. This would be all I wanted to say. If you have any questions, you can ask them.
Thank you for a nice talk. Questions, comments?
Yes, please.
Would you please clarify us the name of chi-squared divergence?
Chi-squared is an F-divergence defined for a specific choice of F.
Does it have some links?
Well, here. It is not usually used per se, however, it is sometimes applied in a Cramer-Rao type lower bounds. But the connection is not straightforward. It requires metrization of a space of parameterized probability distributions, curvature, and Cramer-Rao metric tensor. And so I omit it here, but if you are interested, I can provide you with literature on this topic.
And one more question, please. Can you please explain us how Variational transform was it here?
We used it in the proof or our second theorem. We needed to provide a lower bound for chi-squared, and so we applied the Legendre transform, computed the joint function f, and substituted this into a variational representation. And after this, decomposed this supremum and obtained a nice lower bound for chi-squared.
Okay, thanks a lot.
Yes, please.
So you basically discussed two examples when f is log and when f is t squared minus 1. And they're kind of previously known examples of this kind of how to measure distance. Are there any other choices of f that would give you something interesting or useful? Just
Yes, the total variational distance is for f equals modulo of t minus 1. And it basically captures the discrepancy of two measures on some subsets of our space omega. It is a supremum, more specifically 1 divided by 2 of supremum of all A, subset of omega, modulo P of A minus Q of A.
yes, but that's again kind of something which is known. So are there, well, of course you can plug in any f in this formula and get something. So are there basically f's that were not used before but that are still useful?
It is mostly an approach that brings together different results in different fields. So we do not obtain something new, but this definition, but just try to connect what
So it's
already
just a
exists.
uniform approach to all these
Yes, yes,
sort
uniform
of,
approach. That's the right word.
distances. Okay.
Еще один вопрос, я по-русски задам. Насколько я понял, вот этот divergence ваш, это какое-то обобщение энтропии Шеннона.
Ну да, энтропия Шеннона — это как бы основное понятие, из которого все пошло, но потом она была обобщена на взаимную информацию, которая через энтропию выражается.
Да, спасибо.
А это обобщение взаимной информации уже.
Формула, которая одна из первых, она похожа на условную энтропию. Есть ли какая-то связь?
На самом деле дивергенция Кульбака-Лейблера иногда называется условной энтропией в литературе, но мне не нравится это название, и оно сейчас не особо используется, потому что сейчас этот термин занят другим немного определением. Ну, это кросс-энтропия, то, что в машин-лернинге называется, но, я говорю, этот термин сейчас немного занят другим, поэтому его все реже и реже используют.
Да, а можно вот энтропия, это там просто средняя неопределенность распределения, ну, условно говоря.
Ну да.
А можно совсем простыми словами вот про вот эти вещи, которые вы определяете?
Ну, на самом деле есть такое правило в теории игр, называется bet your belief. Если вы считаете, что вероятность какого-то исхода, допустим, p, то вам нужно поставить тоже p денег на этот исход, и тогда вы максимизируете свою логарифмическую функцию полезности. А именно ей, как правило, моделируется поведение реальных экономических агентов. Ну, то есть на самом деле это способ максимизировать свою выручку в какой-нибудь азартной игре, если выручка не просто мат-ожидание, а какое-то там психологически обоснованное мат-ожидание. И отсюда растут ноги у всего этого дела.
Хорошо, спасибо. Очень интересно.
Что, давайте еще раз поблагодарим докладчика.
Fall. By definition of R sub S, то вам нужно поставить тоже P денег на этот исход, и тогда вы максимизируете свою логарифмическую функцию полезности. А именно ей, как правило, моделируется поведение реальных экономических агентов. Ну, то есть на самом деле это способ максимизировать свою выручку в какой-нибудь азартной игре, если выручка не просто мат-ожидание, а какое-то там психологически обоснованное мат-ожидание. И отсюда растут ноги у всего этого дела.
Хорошо, спасибо. Очень интересно.
Что, давайте еще раз поблагодарим докладчика.